Hello, good morning. So, in the last class we considered second order hyperbolic PDEs and discussed method of characteristics. Okay. So, let us do some examples today and then also proceed to first order PDE. Okay. So, let us before we go for the examples let us check quick recall on yesterday's thing. So, the recall is we considered PDE of the form okay. So, then if gamma is any non characteristic curve, if we take two points, so they intersect the point R. Okay. So, now we have obtained so these are the two equations in two unknowns. So, from here we get x r and t r. Then once we are done with this, we go for okay. So, these two would give P r and Q r, and then ultimately we use du equals okay, of course, the discretized version and obtain right. So, with this let us proceed. So, example, so use method of characteristics to obtain solution of at the first characteristic grid point between x equals to 0.2 and x equals to 0.3, where u is three x along t equals to 0. Okay. Suppose this is a problem. So, this is a given PDE and we are expect to get the solution between these two along the characteristic. Okay. So, solution. So, what are the characteristic curves? So, in this case A is 1, B is 0, C is minus 4 u square and E is 0 when we compare with the standard form. Okay. So, the characteristic curves are M is okay. So, therefore, dt by dx equals to f implies f equals to 2 u, dt by dx equals to g implies g equals to minus 2 u. Okay. So, these are required for us. Now, we have u equals to 0.2 plus 5 x square. Okay. So, therefore, dou u by dou x is 10 x, which is equals to p, and given dou u by dou t equals to 3 x, which is q. Of course, these are along t equals to 0, and so therefore, let us compute u p. U p is u at 0.20. So, this is then u q so this is okay. Then f p is 2 u p. So, this is 0.8, then g q minus u q. So, this is minus 1.3, then C p is u p square. So, this is minus 0.64. So, this is okay. So, having obtained also we need the corresponding data q p. So, we have q which is 3 x, q p is 0.6 and q q is 0.9. So, now let us first compute, we would like to compute first the point. So, this is p and this is q. So, now r. So, we would like to compute this point. So, therefore, we have to use so if we use this, so T p and T q are 0. So, T r is 0.8 . So, this implies x r Okay. So, you can solve the system. So, this is the point. So, now once we get this point, what is our next task? To compute the first derivatives at r. Okay. However, the corresponding equation. So, I am referring these equations. If we recall, so E p and E q. So, for the equation that we have considered, the equation that we have considered. So, I have already mentioned E is 0. So, what would happen if E is 0? In the corresponding equation to compute P r and Q r from this system, this is 0. So, E p is 0, E q is 0. So, there is no contribution from this term. Okay. So, the equations simplified to so by simplifying solving the system we get okay, and we have approximation for u. So, this we approximate by taking the average of p and average of q. So, accordingly we get u r equals to u p plus half p p plus p r So, this if we compute by substituting the corresponding values. Okay. So, this is the technique to compute. So, let us see one more example where E in this case E is 0, therefore, there is no contribution laterally. Even though we have obtained this point, that was not used to compute this. However, to compute to u r we have used. Okay. So, the next example okay, then u t and the points p is this and q is okay. So, now comparing with the standard form, a is 1, b is 0, c is minus u, e is 1 minus x square. U p and u q okay. Then p dou u dou x. So, this would be 1 minus 2 x. This implies p p is 0.6 and PQ is 0.2, just you substitute the point P and Q, then Q 0. So, this implies QP is 0, QQ is 0. Okay. Now, let us go for the characteristic equation. So, characteristic equation, the equation we have. So, A is 1, B 0, C is minus u. So, therefore, this implies m square minus u equals to 0. Okay. So, therefore, f equals to root u and g is minus root u. Okay. Now, let us compute f p. So, this is then f q, f q is p is 0.2, q is 0.4. So, f q is root okay. Then g q is minus okay. So, now we have to find XOR TR, because this is the next task to find R. Okay. So, TR is so, this implies we get XOR and TR. Okay. So, I have pre-calculated by considering some random values. So, you must verify this. Okay. Now, along the characteristics, we have the relations okay, AM dP so the corresponding discretized versions if we use, then we get A is 1, I am just substituting the corresponding values, nothing else. So, we get PR is QR is okay. So, now the next task is to obtain along P r u r. So, this will be u r equals to 0.16, this is u p plus so this implies u r equals to 0. Along q r u r. So, along q r so they are close because u r must be same. Okay. So, they differ by small error. Okay. So, this is the method of characteristics for the second order PDE. Okay. So, now let us make use of the characteristic properties and then try to see the numerical solutions of first order PDE. Okay. So, the story is more or less same. So, before we go to the numerical, so these are nothing but quasi linear first order. Okay. So, we have to review a bit. So, this is the first order we considered yesterday as an example of convection of fluid particle kind of. Okay. However, there the scenario is different, A is not constant. So, u is dependent and x and t are independent variables. So, now more general is something like this. So, this can be put it in a matrix form, right, where A is okay. So, we revisit this when we solve discuss numerical method for system as well. Okay. So, now in this, if A I j is constant, then B I is constant, then the equation is linear constant coefficients. Okay. However, if A I j is A I j x t, B I is B I x t, then linear variable coefficients. If B depends linearly on u, okay, so then linear, okay, depending on other coefficients, okay, variable, but it is linear. If A is depending on u, so then it is quasi linear. Okay. So, examples. So, we discuss numerical solution of this little later. So, this is a linear advection. Okay. Then so this is inviscid Burger's equation. Okay. On the other hand, more generally, so these are partial derivatives, this notation. So, where dou f by dou x okay, and this if we call A of u, the system reduces to, so this is more general. Okay. So, now the characteristic concept, before we proceed, first order also can be classified, okay, depending on the characteristics. So, we must discuss that. So, the eigenvalues of A lambda I are solution of the characteristic polynomial. Okay. Now, let us consider an example. Suppose a system is given by this, and it must be coupled, rho naught is constant, A is constant. Okay. So, then this can be written as u t plus A u x equals to 0, where A is given by 0, rho naught, A square by rho naught. Okay. Then u is okay. So, now if we consider the eigenvalues of this matrix, we get lambda 1 equals to minus A, lambda 2 equals to A. Okay. So, now similar to second order, one can define depending on the eigenvalues. So, the definition is as follows: a system of the form star is said to be hyperbolic at x t if A has m real eigenvalues and the corresponding set of m linearly independent eigenvectors we can call K m. So, this is said to be hyperbolic at x t if A has m real eigenvalues. Now, the system is said to be strictly hyperbolic if lambda I, yes, you are right, lambda I are all real distinct. Okay. So, with respect to first order also one can classify. Then suppose you consider another example which is quite popular. Suppose you consider CR equations, okay, Cauchy-Riemann equations. Then u x equals to v y, u y equals to minus v x. So, this implies A is okay and u bar is u v. In this case lambda square is minus 1. So, no real eigenvalue, hence this is elliptic. So, we have extended the concept to first order equations as well. Okay. So, now the characteristics of first order, as I mentioned, what is the property of characteristic? Okay. So, if you are taken an initial point, so characteristic curves are given by this. So, if this is x naught, so this is x equals to x naught plus a t, where a is slope. Okay. So, these are the characteristic curves, right. So, what will happen? Characteristic curves in some sense they reduce PDE to ODE. Okay. So, and then one can obtain along the characteristic curve. Okay. So, this is 0, right. And what is the ODE? The ODE is, you see here A. So, the ODE is dx by dt equals to A. Okay. So, now similar to second order, we would like to discuss briefly how do we proceed to compute solution along characteristics. Okay. So, method of characteristics first order quasi linear. Okay. So, we consider A dou E by dou x plus B equals to E. So, as usual A, B, E are functions of x, y, u, but A, B and E. So, they are functions of x, y, u, but not of u x, u y, okay, but not of u x, u y. So, this equation is nothing but A p plus B q equals to E, right. So, now what is our aim? the question given u on C, is it possible to determine P and Q on C such that star is satisfied, okay, where C is non initial curve. Okay. So, that means this is an initial curve, then this is C. Okay. So, if u is given on this, is it possible to determine P and Q on C such that the star is okay. So, the answer is true like second order. So, where in this case the slope of these tangents is denoted by dy by dx. Okay. So, we have the following scenario: A p plus B q equals to E, then du is q dy. Okay. So, then eliminating P, we have this implies okay. So, this is independent of P. So, this is independent of P. Now, this can be made independent of Q, okay, if zero, then this is independent of Q as well. Okay. So, therefore, curve C is having a slope dy by dx such that A dy minus B dx is 0. This is satisfied. Okay. So, this is the, so that means equation for C okay, equation for C, A dy minus B dx equal to 0 and equation for u along C is Okay. So, therefore, the characteristics or the curves okay. So, before we proceed analytically numerically, let us see a simple case. So, we consider y equals to 4 and say u is known along a curve gamma, which is y equals to 0. Okay. So, now the characteristic curves so dx by y, so dy by 2 is du by 4. So, now let us consider these two. So, by considering these two we get x is y square by 4 plus a. Okay. Then if the characteristic passes through R, okay, characteristic through R. So, this if we substitute x r and y is 0 and we get a to be x r. So, this implies we have a is x r, therefore, we have y square equals to 4 into x minus x r. Okay. Now, along this characteristic, so we have the characteristic y square is 4 into x minus x r. Now, along this characteristic, the solution is four. This implies now again u is u r at x r 0, which is r. So, this will give us okay. So, therefore, u is 2 y plus u r, right. So, in this case the curves looks like this. Suppose this is the point. So, these are the curves, y square is 2 into x minus x r, along which u is 2 y plus u r. So, if u is known, okay, then one can compute. Okay. So, this is the analytical scenario. So, now we would like to consider numerical integration along a so having obtained the analytical. So, we want to make use of the concept of characteristic and then compute the solution numerically. So, this is in some sense similar to the second order, but let us have a look at it. Okay. So, let u be specified on the initial curve gamma which is not a characteristic curve C through R such that x minus x r is small. So, that this is a gamma, this is C and R and consider a P. Okay. Then the differential equation for the characteristic is A dy is B dx. Okay. That is what we have seen. Then the differential equation for u along characteristic is A du is E dx or B du is okay. So, this implies du is known if dx or dy and ABE are known. Okay. Analytically also we have seen this. So, now how do we go for the numeric? So, first approximation okay. First approximation, this is P. Assume that x p is known, then because we have to approximate A dy minus B dx equal to 0, then E dx. So, this pair goes, alternately another pair could be. So, this we are discretizing A r y p first approximation equals B r x p minus x r. So, this would give, if we know x p, the rest are all known, y p 1 can be obtained. Then from this equation U p 1 can be obtained. Now, second approximation, replace the coefficients A b e by known mean values over the arc R p. So, we consider these two equations, and then we replace the mean values. So, that would be so this goes like this. So, you can, so this is first approximation. What we have done, we consider this equation, then assuming x p is known, we can obtain y p 1, then u p 1. Now, we replace these coefficients by average. You can see A r and A p 1. Okay. So, then we get second approximation from here y p 2. Similarly, from here we get u p 2. Okay. So, that is how we compute. So, let us have a quick look at an example. So, an example, consider this suppose this is the example, then analytical dx by root x dy by u du by minus u square. If we consider this, y is minus log a u, then u equals to 2 at r x r 0. This implies a is 2. So, therefore, y is log. Okay. So, this is, then we consider these two, we get and again we can eliminate. So, therefore, we have 1 by u is right. Then eliminating u, we get log 2 . So, this is the characteristic through x r. Then along characteristic, the solution is u equals to 2 or u equals to 2 root x plus half, either from here or from here. Okay. So, now let us see numerical. Okay. first approximation. A is this, B is this, okay. Then consider the character solutions, this, okay. So, these are the differential equations for the solutions. So, the differential equations for the solution along, I am using short forms. So, now if we approximate first approximations, u r x p minus x r, okay. So, this implies y p 1 is u r (1.1 minus 1 by x r is 1). So, we have considered x p is 1.1, okay. So, this is x r 0 and this is x p y p, okay. So, our initial condition is x r x p are close enough, okay. So, the decrement is or increment is 0.1. So, this is, so now consider this implies okay. So, now from here we get u p 1. So, y p and then we got this, right. So, second approximation. So, we go for u r plus u p 1 dx x r x p y r. So, this will give y p 2. So, you can substitute the values, then so this into u p 2 minus u r so this will give u p 2, okay. So, this is the numerical procedure along the characteristics, okay. So, the example is a little I mean since I have pre calculated, I have done it, you can verify, okay. So, next lecture we will talk about finite difference methods for first order hyperbolic. Until then, bye.